The next talk is a presentation of the functional Perl heterogeneous binary random access lists, which you can use, for example, to implement efficient typed environments for a well-typed interpreter. The paper is by Wouter Schuestra.
Thank you for that introduction, Jeremy. So my name is Wouter Schuestra, and I'm here to say a little bit about a functional Perl that I published in JFP last year. So let's start by talking about lists. So lists are one of the very first data types that we teach our undergraduates. And they're a great vehicle for explaining concepts such as higher order functions with maps and folds, recursion, or polymorphism. But as our students mature, they typically take one of two career paths if they're interested in functional programming. On the one hand, if they choose to go into industry, they quickly realize that if they need to store any serious amount of data, you need better data structures, such as finite maps or some form of balanced binary tree. Other students might pursue a career in academia, and in that case, they spend their time writing intrinsically typed evaluators for lambda calculi or any kind of fancy thing like that, which requires a list where the values stored in the list might actually have different types. And to do this in a type-safe fashion, you typically use something called a heterogeneous list, or H-list. So this paper asks the question, can we have our cake and eat it? Can we define a data structure that's both heterogeneous and efficient? And this isn't just a theoretical problem. So people who work in kind of industry and academia, such as David Christian and his co-authors at Galois, they wrote an experience report on dependently typed Haskell in industry last year that they have this experience of profiling Crucible that showed that linear access imposed an unacceptable overhead on the simulator. As a result, they actually abandoned the type-safe dependently typed approach that they were taking in favor of data.map and unsafe coerce. So what's in the paper? So I show how to implement a heterogeneous binary random access list in ACTA. And this has the same API as just regular heterogeneous lists. So there's an empty structure, nil, and there's an operation to add new elements to the front of the list, and an operation to access elements within the list, a lookup or a bang bang. And all of these operations are both total and type safe. And furthermore, there are no coercions or lemmas necessary for everything to type check. It's intrinsically typed by design. So in this talk, I won't try to cover the whole paper, but instead I'll just focus on the homogeneous case, where we have binary random access lists originally proposed by Chris Okazaki in his book on purely functional data structures, and show how to implement that in AGDA in a kind of total and type-safe way. And then the heterogeneous version follows quite naturally from this. So if we need better than linear access times, we need to shift from lists to trees. And for the moment, let's just make the assumption that we only ever have to store 2 to the power n elements. And that's very easy to do because we can store 2 to the power of n elements in a perfectly balanced binary tree of depth n. So here are a few examples of such perfectly balanced binary trees where I'm going to draw black dots for the leaves storing data and white dots for the nodes which store no data. If I want to write this in AGDA, I can define a little data type for my trees indexed by a natural number corresponding to the depth of the tree. So I can have a leaf which stores an element of type A and has depth 0, or I can have a node which has 2 subtrees of equal length and then returns a tree which is 1 deeper. Now if I want to kind of denote any particular value in such a tree, I typically use a path through that tree. The data type path here is just isomorphic to a vector of Booleans, but it's nice to have this separate data type. And the idea is that this path tells me for every node whether I should go left or right. And then I can define a lookup operation which just follows that path through the tree, going to the left subtree if the path starts with the left constructor and the right subtree if it starts with the right constructor. At the end of the path, I know that I'll have hit a leaf and I can return the value stored there. And the important thing to notice here is that the type indices ensure that the depth of the tree and the length of the path coincide, so I can always return a value of type A. Now, if I only ever had to store 2 to the power n elements, this would be the end of the talk. But you'd be very right to complain that I can't just assume that everything is a power of 2. But there's one observation I can make, which is that any number can be written as a sum of powers of 2. Using its binary representation. And that's the key idea behind these binary random access lists. So a binary random access list consists of a list of perfectly balanced binary trees of increasing depth. And at the ith position in this list, there may or there may not be a perfect binary tree of depth I. So let's look at some examples. So if I need to store 3 elements in a binary random access list, I can do this with a leaf followed by a binary tree of depth 1. If I need 4 elements, I omit the first 2 trees, but I have a tree of depth 2. If I need 5 elements, I have a leaf, I have no tree at position 2, and I have a tree of depth 2 at the second position in the list. I guess if you're familiar with binary numbers, you can see how this works. So a number's representation in binary determines the shape of the binary random access list storing that many elements. So we'll need some binary numbers. Let's write that in AGDA. So we can have a simple type for binary numbers, which zeros and ones are the end of the binary word. And then we can define a successor operation which increments the binary number. The important thing here is that we have the least significant bit at the beginning of the binary number. So if we see a 0, we can flip it to 1. If we see a 1, we flip it to a 0 and recurse. So now we can finally kind of define our random access lists. And there are 3 type arguments that you can see here. A type A, corresponding to the type of the value stored in the random access list, the number n, which is the depth of the list as we're going down, and a binary number, which kind of represents the shape of the list, or the random access list, but it also kind of counts the number of elements in this list. So there are 3 constructors. So nil is the end of the list, and the kind of corresponds to the empty binary word. If we're kind of using a 1, if the binary number starts with a 1, we have a tree of depth n and a tail which kind of has the shape of the kind of binary, the remainder of the tail of the binary word. And if the binary word starts with a 0, then we have no tree, but we have kind of the tail of the random access list that we might still have. So the binary number counts the number of elements and determines the shape of our random access list. And one thing which you can see here is that the number n, it grows as we go down the list. And this is not what you might be familiar with if you're used to things like vectors, where the vector, the number kind of counts down to the end of the list. Here n counts up as we go down the list because there are kind of increasingly deeper trees as we go down the list. And typically we consider random access lists starting with n is 0, but it's good to be a little bit more general sometimes. So now we can define a data type for positions in a lookup function. And these positions, they kind of take a natural number and a binary number. And these positions they essentially combine the usual kind of linear position in a list and the path in a tree. So if we know that the binary number corresponding to the shape of the random access list that we're accessing starts with a 1, then we can choose to have a path of length n in the tree at the head of the list. That's what the here constructor does. The other 2 constructors there, they basically jump over any kind of tree which may or may not be there in the kind of outermost list-like structure until we find the tree that we're looking for, and then we have the path in that tree to one of the individual elements. And then we can define a lookup function in kind of quite a straightforward fashion now. If we want to add new elements to this is a little bit tricky. The first thing you might try would be to define a cons function, which takes an A, which takes a random access list, kind of starting with depth 0, and then kind of produces a new random access list where we have 1 more element. So we've kind of incremented the number of elements, which was represented by the binary number B. But if we try this, we get stuck quite quickly. As we kind of need to make a recursive call, the tail of the binary random access list actually has larger trees, and we're trying to add an A, which kind of no longer lines up somehow. So the solution is to define kind of a more general operation, a cons tree operation, which adds a tree of depth n to a random access list, starting with n, and then increments the number of elements stored. And then we have the degenerate case where kind of n equals 0 then corresponds to the cons operation that we have up there. But if you want to know a little bit more about that, the details are in the paper, but the cons tree operation closely mimics the kind of successor operation on binary numbers. So to wrap up a little bit, we can extend this to the heterogeneous case by writing a heterogeneous binary random access list indexed by a random access list which stores some type information for some universe U. And despite the apparent complexity, there's an example in the paper where I write an efficient lambda calculus evaluator using heterogeneous binary random access lists. And this turns out to be no harder than just using kind of heterogeneous lists as you would in a usual situation. Furthermore, it's fairly easy to port this code to Haskell. It turns out that you only need about 130 lines to define the data structure, the nil, the cons, and the lookup operations. Of which I should point out that maybe 10% is language extension pragmas, but there's nothing too fancy going on there. So in conclusion, if you can choose the right data structure, and one very nice thing about these binary random access lists is that there's no rotations involved, everything kind of stays in the same order. Regardless of when we add things, it kind of stays well formed. And if we choose our type indices in such a way that we can enforce the key invariants that we're interested in, this ensures that all of our definitions can go through quite cleanly, and we really can have our cake and eat it.
Thanks, Wouter. If you're watching the New York stream in Clowder, you should now see a Q&A link where you can ask Wouter questions by video chat.